Hello there. So, we have in the last few classes been discussing about wind energy. We will do so for another couple of classes which includes today, and basically we have had an overview of the wind energy process, and we have looked at what are the geographical aspects associated with it, what is the wind speed aspect associated with it, and how much of a difference that makes. And we also did a lot of calculations. What is the power, how does it relate to the wind speed. We also did the calculation associated with the BETS efficiency. We looked at some parameters associated with it to understand maybe what are sort of limits associated with it, how you should think about it and so on. We looked at the fluid flow through the wind turbine and then came up with that BETS efficiency, which is about 59%. And I also told you that those calculations are sort of the best case calculation, and so typically efficiencies are going to be less than that, maybe 30-40% efficiency you are looking at. It is still a pretty good efficiency because you simply have to keep this out there and it generates electricity for you. I also told you that designs could be different. So, there are some assumptions on the design of the turbine which is used in that efficiency calculation, and therefore, we had one one specific location where the turbine was located, and the interaction between the wind and the turbine took place at that location, whereas you could have other designs where the interaction is spread out across range of locations, and therefore, the interaction with whatever is the forward part of the turbine could be different from what is the interaction with the rear part of the turbine, relatively speaking, relative to the wind direction, and therefore, those factors would also have to be accounted for in your calculations if you really want to get a much more realistic or accurate idea of what is the real limit. So, there are various aspects associated like that, and we should at least be aware, but we have gone through the basic calculation, which is I think a very useful value to keep in mind. And also the fact is that a very large fraction of the windmills that are being put up there essentially conform to this design, that they are horizontal axis and they sort of encounter the wind in one particular direction or in one particular plane, and therefore, the BETS calculation applies to them perfectly fine. So, with that kind of a background, that level of detail that we have developed, in today's class we will look at, we will continue to look at wind energy. We will look more at the parts associated with this wind turbine, and to the extent that those parts have specific applications, we will also look at what are some material requirements that are being placed on those parts, performance requirements which therefore require some material requirements, and therefore, the parts and materials combination is sort of what we will look at, and we will see how that impacts the overall idea of this wind power. Okay. So, our learning objectives for today's class are to become aware of the various parts of a windmill, various important parts of the windmill in the most common design that seems to be getting implemented these days, and to also become to that degree aware also of the various materials being used in the windmill. So, various materials being used in windmills, of course, across various locations in the windmill. So, of course, this term windmill itself is a general term, often in fact in the context of electricity generation they tend to use the term wind turbine because there is a turbine associated with it, but I think in commonplace usage we could still call it a windmill. So, that is in that context this term is being used. Okay. So, with that idea of our learning objectives, we will take a look at the windmill, that the various parts of the windmill. As I told you also that we saw in one of our earlier classes that you could have this vertical axis wind turbine, in which case you do still have some kind of a tower and something at the base, but then many of the parts are in the base itself at the ground level. But most of the turbines that we see these days are horizontal axis turbines, and for them many of the parts are placed on top of the tower. So, this is the general design philosophy that is followed with most of these wind turbines, and it seems to be getting followed across a wide range of manufacturers. So, that is something that we have to contend with, and that is something that we will keep in mind as we put the diagrams together. Of course, I also pointed out that we had this relationship that the power is proportional to V cube. So, much of the design of wind turbines strongly acknowledges this aspect, that the power is proportional to V cube, and therefore, both in terms of sighting of the wind turbine as well as the general stature of the physical stature of the wind turbine is designed specifically to take advantage of higher wind speeds, and therefore, those structures are typically pretty tall. So, that is something that we will have to keep in mind. Okay, so with that background, let us put down some parts for the windmill. So, I am just going to draw a rough sketch, label some parts, and then we will discuss what we are interested in looking at. Okay, so we will start by saying that we have the central part, which is some kind of a hub, and then from that you have a blade. So, a blade will typically have, so let me just clear this. So, something like that. Some design like that, and something like that. We will keep that for the moment, and then little further down the other major part that, so this will be the blade. So, there is a third blade, I will just put that down in the end so that we get this diagram completed. A little bit behind it is a structure that looks something like this. So, this is actually a brake, sort of similar to the brake you would see maybe in an automobile or something. So, it is a braking system, and then further down we have something like a gear. Basically, we do have a gear. So, you will the teeth of the gear would be there. And then further down we have a generator. So, that links up to this gear. So, that is our generator, and we also have a system down here of some form here, which is just I am just drawing this as a schematic, some kind of a system down here, which we will talk about in just a moment. And through all this we also have a shaft. Okay, so, that is what we will have there. And yeah, and then we have a tower. Okay, so these are our major parts, and of course, we will have the third blade somewhere down there. We are only seeing part of that blade here, and that disappears behind somewhere there, something like that. That is your third blade. Okay, so these are the major parts of our wind turbine, just a schematic of it. So we just go over it. So this would be our let me just. So this is our rotor blade. That is the primary part of the wind turbine. That is what interacts with the wind to get us the breeze. This central part here is referred to as the hub, and from that you have a shaft that comes through, some kind of a drive train that comes through. Of some sort comes through. What you have here, this arrangement that you see here is the brake. Then we have a gearbox, and it is the one that enables the linking to the generator. So the generator sits here. And then we have a mechanism here called the yaw mechanism. That is what is sitting there. This tall structure here is the tower. Okay, and finally, what we have here is the nacelle. Right. So this is nacelle. So that is what we have here. So these are the major parts of our the wind turbine, right. So we will actually look at all of these parts. We will try to understand what material restrictions are there and what requirements are there. Pretty much all the major parts we will look at. So if you look at it, the wind, the rotor blade is what interacts with the wind, so to speak. So that is the first and primary part of the windmill. There is a hub which holds all the rotor blades together. That is what this hub does. So this rotor blade is attached to the hub, and then from the hub comes the drivetrain, to which is attached the brake. We discussed in one of our earlier classes that if the wind speeds start exceeding about 70 kilometers an hour, then for most of the existing windmill wind turbine structures, that is quite dangerous. So it can actually damage the wind turbine, the blades, and therefore you need a braking mechanism to stop the wind turbine if you want to stop the wind turbine for any reason. It could even also be for routine maintenance if you wish, but in any case for these to deal with the situation that you may have very strong winds, you do need a braking system to stop the windmill if you desire to do so. So the braking system is there. Then there is a gearbox. We will, as I said, the primary purpose of the gearbox is to link the rotors, the rotating blades to the generator. You can ask why not directly connect to the generator. So again, in fact, there is a reason for it. We will discuss that shortly. It has got primarily to do with RPM control, but there are that the idea that you can connect directly to a generator is also not out of the out of the realm of possibilities. So that is also being considered and is also being implemented. So we will look at that. Then there is this arrangement. So that is the generator that is sitting there. All of these parts, the especially the drivetrain, the brake, the gearbox, the generator, are all housed in this structure called the nacelle, which is the outer covering, so to speak, of this structure. Then at the just below it, you have the tower, or at the bottom you have the tower, which is the tall structure which holds the all the top items, all the items that you just saw are held on top of this tower, and the tower can be quite tall. I mean, if you see the modern designs of wind turbines, you are already looking at blades that are approaching say 50 meters, 60 meters in length, and therefore the tower is actually taller than that, because at the lowest point you do not want the turbine to be the blades to be close to the ground, to hit something on the ground, or be unsafe for any such reason. Plus you also wanted little bit off the ground to ensure some steady flow of wind even at the lowest point. And therefore usually the blade itself is the lowest point of the blade when it comes in that circle is still several tens of meters off the ground. So you are looking at tower structures which are of the order of 100 meters. of the order of that 100 meters length is what you are looking at. There may be, I mean, you can have variation, it really depends on your wind, the windmill blade, but you are looking at this kind of a number, maybe 60 meters, 70 meters, 80 meters, something like that, some several tens of meters, usually more than 50 meters is what we are looking at. Now, as you can imagine, when we discuss this idea of a horizontal axis versus a vertical axis. So, I pointed out that in the horizontal axis you have the tower and the axis is like this, pointing towards the wind, and this is horizontal axis. You can also have vertical axis where the axis is pointing upward. So, when we discussed horizontal axis versus vertical axis, I pointed out that when you have a vertical axis and you have the blades oriented such that the axis is vertical, then orienting it with respect to the wind does not matter, because the wind is anyway always perpendicular to it, right. So, the wind is always perpendicular to it, it does not matter from which direction it comes, whether it comes from the front or from the right or from the left or from the back. The axis is vertical, the blades are rotating about that axis in this direction, and therefore, it does not really matter which side the wind is coming from. So, there is no issue of orientation, whereas in the horizontal axis, when you have the breeze coming from in a horizontal direction, based on which direction the breeze is coming from, the blades have to be oriented so that the breeze comes perpendicular to them. Okay. So, only then the blades can completely benefit from the movement of the wind. So, the blades have to keep getting reoriented based on the wind direction, which could change season to season and typically will change even during time of the day, based on especially based on your location. If you were closer to the coast, you may have sea breeze at some point, you may have land breeze at another point. So, you will have distinct variations in the direction of the breeze, and you need to reorient your turbine. So, therefore, this top nacelle arrangement, nacelle with all the parts, has to get reoriented so that the blades, these specific rotor blades, can face the wind, and therefore, you have this yaw arrangement. So, it is an arrangement which is fixed on the tower, and it attaches to that nacelle and then rotates that nacelle around so that you get the direction oriented appropriately. So, you need to have some wind sensors, you need to have some control system which decides how much to rotate so that it orients correctly. So, all that is also included in this overall system, which even though I am not showing you the exact those parts here. So, there will be some control system which takes care of all these orientation issues. So, these are the major parts. Now, we will go through most of these major parts and try to understand what are some specific restrictions associated with those parts, and to that degree also some aspects associated with the material issues associated with these parts. Okay, so typically if you see this is a sort of a summary, we will come back to the summary again as we close the class. So, typically for example, the rotors, many of the companies these days have been using glass fiber reinforced plastics. So, plastic based blades, rotor blades are being made quite regularly. So, the most common one that you typically see as if you drive around and see wind turbines, certainly in most places in India and even internationally, they are some plastic based blade that you are seeing, and the glass fibers are included there to give them good stiffness and strength, and people are looking at various types of fibers. Usually you are looking at high strength and high fatigue. We will talk about these in a short while. The nacelle houses all of these, the yaw drive that we spoke about, and there is something for blade pitch change. We will look at that shortly. Coolants, brakes, bearings, shafts, controllers, and it has it could be made of steel or aluminum or other such materials, and would also have such parts in it. The gearbox has something called epicycle gears. We will discuss that shortly, but it may get eliminated. So, that is again something that we will look at shortly in this class. Most of the generators are requiring permanent magnets, and so this magnets are present, and you have a fair bit of copper inside that permanent magnet. and the tower itself consists of either pre-stressed concrete or steel or some combination thereof. So, broadly although I am going to get into the details of most of these parts in just a moment, this slide sort of captures a reasonable summary of what you are going to see, and then we will look at them in greater detail. Okay, so if you actually look at these parts and I also got together some data which tells us what is the relative cost to weight ratio. Okay, so if you look at that, you have here the rotor, the nacelle, the gearbox, the generator and the tower. So, if you look at it, if you take the tower for example, it is an extremely heavy part of the structure. In fact, more than almost 50% or even more than 50% of the weight of the overall wind turbine is essentially the tower. Okay, so, the tower is pretty much the main heavy component of the structure, and so if you look at cost to weight ratio. So, if I have cost by divided by weight, it has very high weight. So, it has some amount of cost, but significantly more weight is there. So, relatively you have lower cost and higher weight associated with the tower. It does have cost, it is not that it is free or any such thing. In fact, in terms of transportation costs and all, there are a lot of things involved with the tower. So, cost to weight, if you see, that is it. The generator actually is in the scheme of the overall scheme of things, relatively the cost is more, and as a fraction of the overall weight it is also reasonably heavy, but it is not that heavy. So, the generator has this kind, so you can see the cost factor is higher, weight factor is a little bit relatively less. The gearbox is also similarly it is only one small component relatively speaking in terms of the overall structure. So, weight is also somewhat mediocre, the cost is also mediocre, and I will say that the gearboxes, there is a very large industry which makes gearboxes for a wide range of applications. So, in terms of mass production, gearbox is perhaps the relatively less costing component, simply because there is such a large industry which produces gears for so many different applications, automotive applications and a wide range of other applications require gearboxes. So, gearboxes are available in sort of a generic form, or at least you can order a particular gearbox and it is not going to be that complicated for some manufacturer to make it. Of course, specifications may be different, so you might have to make something specific, but the industry is already in place. The tower on the other hand is very specific to the wind turbine. The specific tower that you use for the wind turbine is an on-site construction in many ways, and therefore, of course, the materials you use are common materials relatively speaking. So, you are using concrete and so on, but it is still it is something that at least has to be assembled block by block in that location or built in that location. Generators also are available in a wide range of capacities. Several tens of kilowatts to megawatts generators are available. So, again there is an industry associated with that from where you can get it. The nacelle and the rotor, the nacelle is basically just the casing and the box that holds everything together. So, that is of course going to be specific to that particular wind turbine. So, but it is not I mean it holds everything together, functionally it keeps everything enclosed and compact. But beyond that it is not an very expensive part of the turbine, so to speak, and even functionally it is not the most critical in terms of the requirements of the overall turbine. The rotor on the other hand is very functionally very critical. So, this is most critical. In some fundamental sense it is most critical because the design is very specific to the wind turbine. I mean, of course, it makes use of aerodynamic principles which are there, I mean which are common across a wide range of technologies, but it is in terms of sizing, you typically do not have blades this size being used for almost anything else. So, manufacture of this blades is a challenge. You need to make 60-meter long blades, which is not a common thing that is done in most places. So, that takes some effort, and so there are companies which specialize in it. So, it is not a mass market product in the sense that you do not find a wide range of companies making these blades. There are companies which specialize in this kind of activity which make these blades, unlike say gearboxes. Gearboxes also, if you want to get technical about them, are sophisticated piece of equipment, but it is not, it is still distinctly more commonplace because a wide range of technologies use them. But these blades in the manner that they are made for the windmills or wind turbines are exclusively only for the wind turbine. So, the wind turbine industry is the pretty much the only customer for the blades of this nature. And it is also the first part that interacts with the wind, and therefore, it defines many of the characteristics that required of the rest of the turbine and places limits on what the turbine can do. It also places an upper limit in terms of what we can expect from the turbine. So, given all this, that is perhaps the most critical part of the wind turbine, and even in terms of costing, it is significantly expensive. Okay, so if you look at rotor blades, so we will start with the rotor blades and see what materials are used, what are some issues associated with them. In fact, commonly these days, as I mentioned, composites is what is being used. Mostly it is glass fiber reinforced, but people are also looking at other reinforcements. So, you can have carbon fiber based carbon fibers can be used. Carbon nanotubes are something that people are looking at, primarily to ensure that it has light weight and many other properties, but lightweight and strength are two dominant properties, but many of the other properties are also there. We will discuss them in detail in just a moment, but glass fiber and carbon are significantly being used. You may wonder why we mention steel and aluminum. It appears to be a little bit old fashioned, but actually it is both old fashioned and current. So, in many ways the metal industry is like that. We always keep thinking that you can get by without the metals and move away to something else which is all plastic and so on. But there are significant both performance issues as well as environmental issues associated with the non-metallic materials, including polymers and plastics that are used. So, the first thing, most important thing about all these plastics is that since you do not want them to degrade very easily in the environment, you do not want them to get spoiled, they are basically typically not biodegradable, the ones that are used. So, that may not seem like much when you just have one wind turbine being set up in one locality, but if you are looking at trying to power a significant fraction of the world using wind energy, then you are going to have wind turbines all over the place, right. So, it is estimated that pretty soon we will have 15-20% of the world's energy requirements being met by wind turbines, and a lot of countries are pushing hard to get these wind turbines located in as many places as possible. So, then we have an issue. It is not just one turbine, you are looking at hundreds of thousands of wind turbines, maybe even millions of wind turbines distributed across various locations. Again, when it is new, it does not seem like an issue. At that point only the manufacturing issue is there, because there will be chemicals associated with that, and you have to find a way to either consume the chemical completely or dispose it safely. So, that dispose any waste safely. So, that issue is always going to be there. Any of these fibers, glass fibers etc., can be hazardous. So, you have to worry about those glass fibers, carbon fibers etc., you have to worry about those in large scale manufacturing processes. But more importantly, if you put a million turbines out there, or say tens of millions of turbines out there, they will all have some finite lifetime. So, you are looking at let us say 30 years down the road, something like that, let us say 20-30 years down the road, when suddenly these turbines come to the end of their life, say eventually those blades start wearing out or they start cracking up in some way, and then and let us say they reach a point when eventually they are beyond repair. At that point you will have to dispose those blades. Then when you have about 100 million or maybe say 10 million such windmills around, and they are all discarding their blades, you have a huge environmental mess. So, in the form of while you are addressing the environmental issue by using this clean energy solution of wind energy, you have to be aware that the manner in which you use that wind energy should not create a problem again 20 years down the line, right. So, we have to guard against that right away. So, that is where things like steel and aluminum actually still have a significant role to play. So, if you take steel and aluminum, there is no problem at all in terms of recycling it. You simply have to heat it, melt it back, and then you can recreate that blade in whatever manner you want. You can always, or you can even just do heat treatment to relieve any stresses, etc., if it is possible. May not be that easy because it is a longish structure, and then bring it back into service. So, in terms of recyclability, the traditional materials are actually like steel and aluminum are still very promising, and the steel, and there is also a large industry. There is a steel industry there is a lot of machine tools industry, there is a machining industry, etc. So, even if you want to change shapes, you want to get some complex shape, etc., there is a lot of people, there are a lot of people who are experienced in this area, and lot of industries that are there, a lot of machinery that is already in place which can create what you want, and therefore, this is still an industry that competes in almost any technological sphere, and the windmill or wind turbine sphere is not an exception. So, there also you have the metal industry trying to make its case, and I mean people are continuously doing research to see if that can be done. But still, as of now, what is coming out is typically composite. So, that is the largest contributor at this point to the rotor blades. So, what are we looking for? Of course, we are looking for lightweight. This is important because the wind has to push the turbine, right. So, it has to or rather I mean the based on the lift that is generated, the turbine should start rotating. Now, the heavier the turbine is due to gravitational forces, etc., you are basically going to have a lot of inertia, right. So, you are going to have a lot of inertia, you have to push past the inertia and to get this or you have to have enough lift which is over and above this inertia to get this turbine to rotate. So, it may not move as effectively, and therefore, lightweight is a very important aspect of the turbine design. So, inertia is an issue. Okay, so, this inertia is an issue. Fatigue resistance. So, fatigue is actually the idea that materials deteriorate or fail at loadings well below their rated loading. So, you take a material, you do a test, you make a new component, you do a test, you put a tensile test and you pull it apart and see at what level of loading the material fails. Okay, so based on some standards and standards ways of testing, you can say that the failure of this material will happen at this load. If you make this material with these standard dimensions, failure will happen at this load or at this stress value. Okay, some specific stress value it will fail. So, the stress will take care of the cross sectional area, you do not have to worry about whether it is a larger part or a smaller part, all that is accounted for if you look at the stress. It is normalized with respect to the cross sectional area. So, it is load per unit area. Now, that will be some reasonably high value, let us say there is some particular value, and therefore, you feel that this is adequate for the utility that you are trying to put this structure to. But if you have cyclic loading, and almost all components in regular use have some cyclic loading, right. So, cyclic loading in the sense you load the component a little bit, then you release the component. It could be anything. If you are on a vehicle, so the vehicle goes over bumps and various roughness factors in the road. Just because it goes in a poorly built road does not mean all the parts in the vehicle have failed, but those parts have been stressed in one direction and stressed in the other direction repeatedly. But with very small stress levels. The stress level was not so high enough to damage the part, but it did go through an increase in stress, a decrease in stress, increase in stress, decrease in stress, and it may not even have been periodic, it will just go up and then stay up for a little while and then suddenly drop down, come back up, etc. So, you will have wide range of loading. So, people test that for test to see if the materials will fail under such cyclic loading conditions. Okay. So, it is generally found that a vast set of materials actually have a situation where if you put them through cyclic loading, and of course, in a systematic test you put them through a known frequency loading and known load level, etc. When you do that, you find that many of these materials will actually fail at a value of stress which is significantly lower than the rated stress of that material. So, you did the original test and you came up with some value, but under cyclic loading, even though you are loading it up with much less load, just because it is cycling repeatedly over a long period of time, it fails. So, fatigue is a very important and this phenomenon is called fatigue. So, it is repeatedly loading and unloading a structure and it will fail at a value of load significantly less than the rated load. So, the fatigue is very important for most structures which are facing cyclic loading, and a wind turbine is a classic example of it, because wind will come on at some point, wind is not going to be steady, you will have wind velocity is continuously varying even as the over several minutes. So, you will have suddenly slightly faster wind, slightly slower wind. So, you have pushed the blade a little bit more, it comes back to the front direction even as and that is when you have just variations in the wind flow. Even if you take the windmill structure itself, if you look at the fact that you have a blade there and a blade here, and I am just drawing two blades at the moment, and let us say you have a tower here, then clearly the blade that is at the bottom is getting some shielding because there is a tower right behind it, right, whereas the blade at the top is not getting any shielding because there is nothing behind it. So, even if the wind were steady, if you have a steady breeze that is flowing, as the blade rotates through the through its standard cycle, when it comes to the top or for a significant fraction of the cycle, it is not having anything in the back, and so the wind is continuously relatively uniform. But then when it comes down and it gets shielded by the or gets some kind of a blockage effect because of the fact that there is a tower right behind it, suddenly there is a drop in the wind loading on the blade. So, the stress on the blade suddenly decreases. As it comes off the shadow of that tower, it will again go up in loading. So, you are guaranteed that in every circle, every circle that it makes, there will be cyclic loading. You will be loaded up and then you will release the load, you will again load it up and so on. So, every cycle that every time it rotates once, it is going to be loaded once and released after that, and every blade is going to undergo this. So, you are guaranteed of cyclic loading. So, this is guaranteed to happen. If the windmill is operating, you are guaranteed to have cyclic loading. So, this is something. So, therefore, we need to look at fatigue resistance. The strength is the overall loading that is there because of its own weight, the wind that is pushing against it, etc. So, you do need to have significant strength, and you are looking at longer and longer blades because that helps you access more higher wind speeds, etc. So, that is something we have to look at. Stiffness. So, this relates to the integrity of the shape. So, if the blade is not stiff, then it will flap around in the in strong winds, and you have to keep in mind that there is not much of a distance here between the tower and the blade. So, if the blade were to twist too much, it can even hit the tower, right. If it were not so stiff and you could actually go down go backwards. So, if the blade was not so stiff and it could just bend backwards, it can even hit the tower. So, for a wide range of wind speeds, you have to be confident that the blade is stiff enough that it will not go and hit the tower. So, that is something that you have to keep in mind, and that is why again you have some rating, some wind speed rating, and you say that it is only within the scope of this rating that you will use this wind turbine. If the wind speeds are higher, you will stop the turbine. Then there is the issue of how it interacts with the environment. So, given that it is out there, you are not shielding it in any manner, you are just putting it out there in the sun. So, it is going to face a lot of heat and cold. So, cyclic temperature is going to be there, the night it is going to be cold, the day it is going to be hot, there is a lot of humidity, you could have rain, you could have dry conditions, wide range of conditions, and of course lightning strikes. You are going to put this out there and you are bound to have it is guaranteed to have lightning hits because you have put this tall structure out there, and typically in open area you have put a tall structure. That is exactly what is required to attract lightning, and it will get a lightning strike. So, you have to be prepared that materially it is in a position to handle it. There are lightning arresters, there is ways to take the lightning hit down to the ground and have it grounded. Okay, so, this is something that you have to be worried about. And of course, as I mentioned right at the beginning, blade recycling in terms of material recycling, and this is something which may not be an issue today, because today is when we are all into this wind energy field, and every country is putting all this effort to put these windmills out there. If you look 30 years down the line, this is an issue, and this is something that we need to address right away. We have already made this mistake in the past where we said oh, we found petroleum, great, let us use the petroleum. That is exactly why we are in this situation today, that we need to worry about the environment, right. So, 30-40 years of extensive petroleum usage, and we suddenly have this problem, and now we have to do something urgently to deal with it. So, we do not want to wait 30 years and then have a major problem. We would like to address it ahead of time, so that we are, because now we have seen the cycle of how something we use hits us 30 years down the line. So, we might as well plan for it and do something appropriate. So, that is the rotor blades. I spent significant time on it because it is the as I said, the most important critical part of the wind turbine, and the first part that gets the whole thing operational. Then you have the tower structure itself. As I said, mass wise that is the most massive part of the wind turbine structure. The blades are very light, the tower is actually quite heavy. So, it has to actually deal with wind shear. This is simply the variation in wind speed as a function of altitude. It may not be much, I mean it may be a difference of say 10-20 kilometers per hour, something like that. So, for example, if you double the height of the structure, the wind speed increases by about 10%. Okay. So, but at the same time, so it is a difference of 10% of stress from the top of the structure to the bottom of the structure, and it is there continuously, I mean based on the height of the tower. So, you have to have a structure that deals with this wind shear and does not get affected by it. As I said, we are always interested in increasing the height of the wind turbine, because the power available in the wind increases as cube of the velocity of the wind. So, if the wind speed, for example, you double the height of the structure, right, and I said wind speed goes up by a factor of 10%. So, if you have original wind speed was V, we now have 1.1 V, okay, so 10% more. So, what will happen to the power? If you originally had P, if you do the calculation, this is 1.1 into, I mean 1.1 into 1.1 into 1.1. So, 1.1 cubed is what the power will become times P, and that is approximately equal to some 1.3 some 1.33 P, something like that approximately. Okay. So, this means this is approximately 30% increase. By doing nothing, by simply pushing the windmill to a higher location, that is it. You just pushed it to a higher location, it got you 33% or not 30, some 30 plus percent of increase in power. That is a huge increase in power for nothing else changing, everything else is the same. You simply push the windmill up to a higher location, you are getting 30% more power. So, naturally there is a interest to get this windmill to be as high as possible, so that you can get this benefit out of the power that is available, and therefore people try to have tall towers. But at the same time, if you double the height of the windmill, you are going to have to also double, you have to also do something about the diameter of that tower, so that it stays stable, and usually that means 4 times the diameter. These are approximate numbers, they are not hard and fast numbers, and it will really depend on the type of structure you are making and all that. Just to give you an idea, that material required for the turbine is going to, I mean for the tower itself is going to go up significantly if you sort of double the height of the turbine. The material choice will impact things like transportation and construction of that structure, because if you are using for example, there are people who use tubular stainless steel based structures. So, those tubes have to be transported to that site, and in fact with respect to windmill construction, this transportation is a fairly significant activity. Maybe over the lifetime of the wind turbine, the cost is perhaps not that much, it is distributed across the cost of that lifetime, but still transportation is a major activity. If you ever go to one of these sites where they are setting this up, you have to keep in mind that let us say even the windmill blade is say 50 meters long. So, you need to actually have a truck which has 50 meter long carrying capacity behind it, and place this single blade there and then carry it carefully to that site. So, it is a fairly involved activity. They have to ensure that the roads are capable of handling a truck that long. It is not heavy, but it is just long, it is an awkward shape. So, you have to find a way in which that the road will be able to handle this structure, and this truck will have to be guided to that location. So, with respect to the tower itself, people use concrete, it increases the life and is better for taller towers. So, therefore, this is the way in which people are working with it. More specifically, they use what is referred to as pre-stressed concrete. So, that helps increase the life and is ideally suited for taller towers. Interestingly, there are also people who are even relatively recently looking at wood as a way in which you can make these constructions. It has good fatigue properties, and therefore, this is something that they are actively looking at. So, this is related to the kinds of design restrictions and construction ideas and aspects associated with the tower design. Then we will look at the hub. The hub, if you go back to our diagram here, this is the hub, this part here is the hub. Okay. So, this is the central part of the wind blade arrangement. So, it does a specific activity, primarily the blades are bolted to the hub. Okay. So, the blades are attached to that hub. and you could do it two ways. You can actually directly bolt the blade onto the hub, but usually that is not the preferred way to do it. Instead, the blades are actually bolted to something called the pitch bearing, and this pitch bearing is bolted onto the hub. Okay. And the idea is simply that you may have wind may be coming at some velocity, and then the blade will have a particular, we will talk about this, how you angle the blade with respect to the okay. So, how you angle the blade with respect to that wind, incoming wind will actually depend on, ideally it depends on the wind speed. Only then you get the best benefit out of the wind that is flowing. So, if you actually get it fixed rigidly to the hub, you are not in a position to reorient the blade gets stuck in that one position, and therefore it is not ideally suited to pick up the best energy from the wind. So, it is better to actually fix it to some other bearing, which is referred to as the pitch bearing, which would sit somewhere here. So, some pitch bearing that sits there, and using that you can reorient the blade based on the location of the breeze. And in fact, you can also use this to help stop the blades, to assist you in stopping the blades in the event that you want to shut down this generator for some purpose. So, there is a pitch bearing on which the blades are attached, and that pitch bearing is attached to the hub, and then that hub is attached to the rest of the structure. So, this is the other way in which this is done, and so this is the central part of the wind turbine. And then we have the gearbox. So, there is a shaft which comes from the blade, and that goes to the generator, right, and this shaft that goes from the blade to the generator typically does not go directly to the generator, although we are going to discuss that right now. It actually goes through a gear. So, if you go back to our drawing which we just put down, you can see that. So, this is the drive train or the shaft, and this is coming from the blades, from the hub, right, it is coming from the hub, it comes to this gearbox that you are seeing here, this gearbox, and from that gearbox it is attaching to the generator. Okay, so, it is attaching to the generator out here. So, that is where so you can see that it is attaching in this region, right. So, so this gearbox is there to attach the to connect the blades, the rotating blades to the generator. So, why do we need it? Okay, so it is specifically required because if you actually go and stand in front in one of these locations where these wind turbines are operating, you will find that the turbines are rotating, but you can easily see the each blade can be comfortably seen with your eye. You don't I mean, it is not rotating so fast that you don't see anything. Even your the ceiling fan in your house is rotating much faster than the wind turbine is rotating, right. So, typically you are only looking at about say 10 to 20 RPM, that is really all that you are looking at if you are looking at what is there in the what the wind turbine is actually doing as it rotates. But if you look at the generator, if you want to set it up such that the electricity generated by the generator is directly is something that can be directly fed into the grid, so to speak, or with minimal processing be fed to the grid, it is typically desired that the RPM at the generator should be very high, revolutions per minute at the generator should be very high. So, even though the shaft coming from the wind blades is rotating at a lower revolution per minute, you want the shaft going into the generator rotating at higher revolutions per minute, and the difference could be several orders of magnitude. You are looking at some 10 RPM going to several hundred, maybe 1000 RPM kind of situation. So, you definitely need a gearbox. So, that is the reason why you need this gearbox to convert this low RPM coming from the blades to the high RPM required by the generator. So, that is why we need this gearbox. So, in fact, in order to save to reduce the complexity of this of the structure and to make it easier to handle, people are actually looking at gearless or direct drive designs. So, there is a catch there. I mean, it is a little bit of you gain some advantage, you lose some advantage also. So, one of the things that is being done here is then we say that let us not worry about what is being generated by the windmill, let it generate whatever it can generate. So, we will not restrict the wind turbine. So, in some of these geared structures, in some of the other structures where you are trying to get the electricity out from the generator to match what is required, we put actually restrictions on the wind turbine. So, we try to keep the wind turbine within a small range of operating points so that the electricity generated is appropriate. But The other option is to just let the wind turbine generate whatever electricity it can and then work with the electronics later on to get it to whatever condition that you want. So, so that is also being looked at, and more specifically in this case they will what they will do is they will add more magnets in the generator itself, so that you will get the desired frequency of electricity being generated. Okay. So, these magnets are typically permanent magnets, and so neodymium is used, it is a rare earth, and if you actually want these permanent magnets to be increased, you would actually end up having to increase it by a factor of 10 in the number of permanent magnets, and so the overall structure actually becomes heavier. So, even though it is less complex in the sense that you have released removed the gearbox, but it becomes heavier because you have had to put more permanent magnets to help you with this RPM issue. So, that is a mix and match of things, and you are using a rare earth material there, and in fact the stock of the rare earth material is not there by definition, it is a rare earth, it is not commonly available. So, it is not a commonly available material, it is a rare earth. So, you have to worry about it, worry about its availability, worry about how you are going to use it, and if you go this route, then that is a danger you face, because you will run out of that material, and then if you are saying I am going to power a significant fraction of the world's requirement using this approach, you are going to face some limitations. So, right now still geared versions are used, and it is something that we have to stay aware of. So, again as I said, this is sort of a summary of what is being used in the windmill. You could use rotors which are glass fiber based, but as I said we could also look at aluminum, we could look at steel. The nacelle actually houses all of these or has connections to all of these. It has the yaw drives, the blade pitch change mechanism. So, I told you that the hub is helping you change the pitch of the blade, but that mechanism will be housed somewhere in the nacelle. The coolants associated with the whole process, I mean your generator may end up getting hot, so you need some coolants for it. A brake, that brake is what is required to slow down the windmill, or increase the speed of the windmill, I mean not increase the speed, at least release the windmill. The bearings, all the bearings, there are considerable number of bearings that are going to be there, because you have a shaft that is running through, you have gears mounted on the shaft, you have you have the generator attaching to it. So, many places you are going to have bearings. There is a shaft, there is a controller there which takes care of many things, including orienting of the structure. Then I spoke about this gearbox. These days they are looking at something called the epicycle gears, which helps you reach a wide range of RPMs if you try to utilize it. But as I said, they are also looking at options where you can actually eliminate the gearbox altogether, so that the structure becomes less complicated to make, but because of the requirements then getting pushed on to the magnets of the generator, the weight of that structure may actually go up. So, as I said, the generator itself they are looking at permanent magnets and considerable amount of copper that you will need there for all those coils that are being required. So, that is the sort of the material requirement on the generator. And with respect to this tower, people primarily look at pre-stressed concrete and steel. Some people also dabble with other kinds of materials. As I said, recently there was also some demonstration of a wood based structure, which may seem old fashioned, but it has its own advantages and disadvantages. So, this is sort of the overview of the materials used in a windmill. And so, in conclusion, we have just seen that the modern wind turbine has several parts, wide range of parts, which have wide range of requirements, because those parts are serving specific purposes, and in terms of material property itself there is a requirement, in terms of the shape and sizing, weight, etc. there is a whole bunch of requirements, and these are all integrated in a design that places these specific requirements on some of these parts. So, based on the design of that structure, for example the blade, because of the shape of the blade and the size of the blade and the location of the blade, it has to have some properties. The tower has some properties required of it because of the load on it, and so on. And based on the function, a wide range of materials are being used for the various parts of a modern wind turbine. And as you can expect with any technology, this is always a varying this is always an evolving situation, and that is why there is so much research in all of this. There is all these R&D groups both in research in universities as well as in companies that make these parts, which are trying actively to get a better part or a better material which will satisfy those property requirements while also meeting cost, lifetime, recyclability and so on. So, so that is something that is always ongoing, and perhaps you will also get an opportunity to work on it. I must again say that this is a technology that people are pushing hard to set up in large scale across countries, various countries in the world. So, it is actually a very actively growing market with many companies pushing hard to get these products out and be part of this growing market. Okay, so there is a lot of scope in this market. So, with that we will conclude today. We will look at some more aspects in the next class. Thank you.